Good afternoon, everybody, and welcome to the MTL seminar series. And today it's my pleasure to introduce as a speaker Professor Hanseup Kim from Utah, University of Utah. So he did his graduate education in Michigan, then he went on the faculty at University of Utah, and he has been there since then. He is the director of their nano facility. He's a very accomplished person, and we are very, very happy to have him. And he's going to tell all this great work that he's doing on very low power sensing. Thank you, Hanseup, for coming, and go ahead.
Well, thank you. Good afternoon. My name is Hanseup Kim. I am from University of Utah. It is my great pleasure to be here and to make this presentation to you all. And I would like to thank Dr. Luis Velasquez Garcia for your kind invitation. The main topic of this talk is how to minimize the power consumption of a sensor node and how to extend and maximize the lifetime of a sensor node such that sensor node can be deployed in the field where there are no power rails. So currently, the deployment of sensor nodes in the field where there are no power lines are pretty much limited, mainly because we don't have a great source of power for individual sensor nodes. Energy harvesters typically have limited power density or power amounts. On the other hand, the battery, as we all know, have a finite lifetime. So my proposal to mitigate that issue is that we develop a near zero power sensor, especially for gas detection that traditionally is known to consume a lot of power, so that we can deploy it especially in the agricultural settings. So I would like to discuss what we have been achieving in the University of Utah and what kind of remaining tasks are left. So I just want to give you a perspective on the technology in terms of application agriculture. So these are the list of grand challenges, selected by United Nations and so on. And among them, of course, food, energy, environment are very much closely related to agriculture. So any technology, microsystem technology we develop can improve the agriculture. That means we can contribute in a way to mitigating these grand challenges in the humankind is facing. In agricultural environments, biologists have found a very interesting phenomena. It's a plant self-defense. So just like people, when we got punched, we scream, but we scream with a sound. So just like that, when plants get attacked by insects or caught by other type of pests, then it also screams. But instead of sound, they emit particular specific gas molecules out. Once the gas molecules are out, and eventually a bird will smell of it. And then bird starts trying to locate where it is coming from, and then find the location and go there and eat up those insects. This completes the cycle of self-defense, and this is very much amazing natural phenomena. So what we are trying to do as a microsystem engineer is that we would like to get into this loop. So instead of letting a bird smell on it and taking time and finding out where taking care of these ones, if we can immediately smell of it together, then maybe we can immediately notify a farmer who can immediately take actions. If he is able to do so, we can take the early, localized, only as much as needed treatments. So this will lead to not just a crop yield increase, but also healthier soils and healthier crops because we are using the less chemicals, right? And then if these crops are biofuel crops, like sorghums, then we can also contribute to the generating, increase the production yield or efficiency of energy. So now coming back to the microsystem engineer, what is the problem? As I said again, deploying these sensors into the field is a problem because there are no power lines and energy harvesters are not generating enough power. And the only alternative is a battery. A battery has a limited lifetime. So my approach is then how to use the best use of a battery for a sensor node. So the question comes to this one, right? How to reduce the power consumption of a sensor node. We can from the graph, we noted that currently most of the power consumption of a sensor node is being wasted by processing irrelevant sensor data, considering meaningful sensor events are very rare. For example, for one farming season, the herbivore attacks could happen maybe 3 or 4 times only, but to catch those 3 or 4 times, we have to let the sensor turned on all the time. That's why we are consuming enormous of power, 95 to 99% of the power, just because the sensor, we gotta let the sensors run, right? Sensor is on there, it is continuously measuring something, but that have nothing to do with me. So that is the main problem. So my approach is if we can remove that power, and if we can minimize the power to the level of leakage current. The leakage current is 10 nanowatts. That's the CMOS 130 nanometer process. Chips are generally, that's the leakage level of that. If we can lower the powers, sensors operation power to the leakage level, we can call it a near zero power, right? Because it doesn't add to anything. It is smaller than even the leakage power. And so to do so, I was proposing that we would like to have an event-driven wake-up. So sensor is somehow sleeping, doesn't consume power. But if something comes up, then it should be able to catch that. So if we can do it, then maybe we can extend the lifetime to 100 to 1,000 times. That makes these sensor nodes applicable for a lot of applications in the field. So the main question, technical, comes down to this question: how to achieve continuous sensing while we have a dormant or sleeping sensor node. And this is my approach. So I would like to build a chemical switch. The chemical switch is a gateway for the rest of the circuits. So normally it has an open circuit, so it doesn't consume power. But when chemical gases or target gases are detected, then it closes the switch and then let the current flows, and it wakes up the rest of the circuits. So until we detect the gas, the rest of the circuits are sleeping, so it doesn't consume power. So that is the conceptual approach. And then how to implement it, and this is specifically how we are working on. So we are trying to use the nanostructure. So in the nanostructure, we are trying to build the nanogap structure. And it is a very obvious structure, right? There are 2 conductive layers. Between them, there is a space. So it is physically disconnected and does not consume power. But so normally, it doesn't consume power. But these electrodes are coated with some chemical linkers that can capture the target gas molecules. So when the target gas molecules come, and then it is captured by both sides of these linkers, then it forms a molecular bridge that allows the current to flow, and those currents could wake up the rest of the circuits. Of course, this is conceptually simple, but we can all feel that this is a very ambitious plan because we gotta fabricate the exact nanogap, right? It's a sub 10 nanometer gap, which is not easy. And also we gotta synthesize chemical linkers that are fully conductive so that only the electron tunneling should happen when through those captured gas molecules, right? And also we gotta control the length of the linkers, and we should get the high on-off ratio. When it is off, when it is on, the difference should be high enough. Otherwise, we cannot really turn on the electronics directly. So those are the questions that were remaining. So just briefly, if we can capture the if we can capture the gas molecules, as you can see in the band diagram, originally it was an air gap, but we can introduce basically LUMO and HOMO, right? So that therefore we can provide basically the path that electrons can flow when there comes the bias. Another concept is this. Okay, that's good. If you can make the one single switch, still there is a problem, right? Because you have a one single switch nanogap, and in low concentration on the top, you are not supposed to detect anything. But one of those few molecules happen to come into the gap, right? And then say, well, there is a gas. That's not what we want. And also in the opposite side, under high concentration, we are supposed to detect something, but maybe sometimes, gas molecules do not come. So how to solve this issue? Because gas molecules move randomly, and it is very difficult, impossible to control them. So our approach is to use the statistics. So if we can make these nanogap sensors in the array, as you can see, that there are a lot of boxes. Those boxes are, let's say, one single nanogap sensor. Then the white box is the one with the open gap, so it is disconnected. And then yellow one is the one who already captured the gas molecules and became the conductive. So in low concentration case, however, whatever the pattern of landing is there, still there is no path between one electrode to the other electrode. But in higher concentrations, whatever landing pattern we have, there will be always a path from one electrode to the other electrode through this path. So basically, by building the array, we can build a passive switch. In low concentrations, the probability of a connection is always 0. In high concentrations, the connection probability is always 1, and between them there is a sudden change. So it looks like, the plot becomes like a switch. So this phenomenon is called the percolation. Of course, I studied a lot in physics and chemistry. And then by using the percolation structure, we would like to control the collective control of randomly moving multiple particles into multiple gaps. So that's one way of we are doing. So then the next question is, if you have a percolation structure, how do you control, how do you make it more deterministic, right? There is a slope, and then we want to make the slope as steep as possible for a better switching capability. So through the Monte Carlo simulation, we realized that as we increase the size of the array, we can make it more steeper. So that means we can make it more deterministic switching. What about the threshold? Above a threshold, it will get turned on. How do you modulate it or manipulate it as a designer? So again, that becomes possible by controlling this degree of freedom. So when I make these arrays, one island can be connected to 2 ways or 4 ways, 8 ways, 16 ways. By controlling that, we can move these threshold points and manipulate it. So by combining these theories and concepts, then now, next step is, of course, making the fabrication of the structure. In my days, and maybe Louis's days, we used to do 17 mask processing, and nowadays we do only 1 or 2. And this is a case for this as well. So the structure is pretty simple. So we have the gold electrode at the bottom and top. In between, we put a sacrificial layer. That sacrificial layer thickness is very important because that decides the distance that needs to be. So, and then we etch from the side, then we can form the gap. So as you can see at the top, that's the device fabricated. If you look at the gap here, a little bit here, then that's the top view is this, and the gap is formed around the top electrode hanging over the bottom electrode. And the TEM, transmission electron microscopy, is showing that the gap is 5.2 nanometer. That's what we want. Of course, here, probably I'm not going to spend much of time here, but making exactly 5.2 nanometer gap is really, really challenging. So right now, if we have a tool called the ALD, atomic layer deposition tool, they can deposit materials atomic layer by atomic layer. But that doesn't work under 10 nanometer for those of you who have used it. So when you deposit the ALD layer and then try to make a gap, typically side walls, it turns out that there is no gap because there is not sufficient ALD deposition. So what we did was we manipulated the ALD tool by exploring so-called exposure mode. So by controlling temperature, dosing pulse, dosing time, and purging time, and then valve control. Typically in normal mode, every valves are open all the time. So we were able to push out this one, and there was able to form the sideline gap clearly. And then on the right side is showing the distribution of the thickness, which is showing about 3 angstrom, 0.3 nanometer difference. So we can now get pretty much uniform nanogap. So after that, of course, we needed to build the 2D structure. And then 2D structure looks like this. We are forming the top electrode and bottom electrode skewed by the half the distance of the sides, electrode sides, so that top electrode can be connected to 4 of these bottom electrodes. And then the bottom electrodes can be connected to the 4 of the top electrodes, vice versa, so that we can have a connection from one side, bottom side to the top side, and top side to the bottom side, and bottom side to the top side. In such a way, we can make the connection if the right components and right gap is filled with these gas molecules. And then, of course, we had to develop the chemistry. I'm not a chemist, so I don't know that well. But we had the collaboration partner, Professor Ryan Looper. His group has been developing these linkers. So something that I need to mention is that these linkers consist of triple bonding and benzene ring. The reason is triple bonding and benzene rings are all very, very conductive. So therefore, when electron hopping or the tunneling happens, we can regard it from here to here as just a conductive path. So we don't need to worry about that part. And by having the connecting multiple benzene rings, we can control the distance or the length of the linker. So another thing is that if you have the benzene ring and triple bonding, then it is a very stiff. So it doesn't bend. So therefore, we can easily expect what would be the length inside the gap. So after that, these are the results of the single nanogap sensor. So normally, the blue line is the normally, when this is disconnected, that's the power consumption and current. So as you can see, current level is about 10 picowatts. And then, but once it captures the gas, suddenly it jumps from the blue line to the red line, depending on the bias voltage. So the difference on-off ratio is becoming more than 1,000, more up to the 10 million times. 10 million times is very close to the kind of a worst switching ratio of a mechanical switch. So it is getting kind of close to that. Of course, there is in red line, if you look at it, there is a jump. Why that is happening? Probably it's because of the tunneling, right? Initially, our band gap structure looks like this. And then as we apply the bias, it became the trapezoidal shape. And then if we apply more voltage, of course, it becomes triangle so that it becomes easier for electrons to transfer. And then also, we confirmed that it is very sensitive to the gap size. So if you don't have the right gap, then you cannot detect the gas. So if a gas molecule is longer than the remaining gap, it does make the bridge. If it is too short, also it does make the bridge. So only when the gas molecule has the right size, then we can make the gap. So that adds the selectivity. That's why this sensor provided a better selectivity than just chemistry-based sensors that you see. So this is a selectivity. As you can see, we tested against all different kinds of groups, chemical groups, alkene, alkane, phenyl, and so on. And then as you can see clearly, there are significant selectivities there. And we changed the length of linkers, 1 benzene ring linker, 2 ring linker, 3 ring linker, and that shows that we need a kind of exact length to detect to capture and detect a gas. So the final question is, so what? Can you connect it? Can you turn on and off the electronics or not, right? So we connected it to the circuits, and then obviously we can kind of turn on and off the rest of the circuits very well. And this is for the slide for those ones who are interested in chemical sensors only. Always for the gas sensors, humidity is a big issue. Whoever develops gas sensor, humidity is your biggest enemy. So what we did is we developed the package. So that sensor is now located here, and then we developed the package. So left and right, there is a chamber that is located to hold the hydrogel, which works as a sponge when the humidity comes in. And on top of it, we have a cover, but if you look at it carefully, there are small holes. So we made a mesh so that we kind of big water particles can be filtered out. So based on the testing, we can make this sensor work up to the 99% relative humidity up to 4 hours. Beyond the 4 hours, we cannot protect it further. So I would like to show you some video to wake you up. And we put the gas in, and this is our device. It's hard to see, sorry, because of angle. So originally, its resistance value was about hundreds of gigapascal. And then once you take it out, then its resistance goes back to 100 mega ohms. So that means more than 10,000 times switching is happening. So if we and then if we put it back, it goes back to the high standard. So if we move a little bit fast, then we place the sensor inside the chamber. We inject the target gas, and after some time, as you can see on the left side, so you can see here, it is a self-detecting. It was always off, but when the gas comes, then it wakes up. So of course, after that, we made the 2D arrays. And then 2D array, what it does is the uncertainty becomes less and less. So as you can see, the area or the distance between the top line and bottom line, as you increase the size, of course, those gaps are becoming small. So it becomes more reliable, as we mentioned before. Of course, what we are losing is the minimum threshold we are losing, and we need a higher bias voltage. So because of these two reasons, we moved on to the now 3D. 3D will reduce the bias voltage because it provides the parallel path, and then it automatically gives a larger degree of the freedom, so that's why we can lower the threshold as well. So we made the 3D structure, and we simulated where the electrode location should be, but it turned out that it didn't make much difference. And as you can see, we just repeated the same process, and now we have multiple gaps. So once we have the 3D layer, of course, as we expected, we were able to lower the bias voltage. Why do we need to lower the bias voltage? If it goes more than battery's voltage, then we got to have an additional circuit voltage booster. That means we got to spend more power. So it's not going to be a near zero power sensor. And then we were able to lower the threshold volt again. And then 3D array also works pretty well as a switch, as you can see. It works more than 10 times. That is sufficient for agricultural purposes. So far, in summary, we were able to prove that the nanogap structure can be used for gas detection. And the tunneling really works. And then that tunneling-based switching can turn on and off the electronics. And then, if needed, we can make the 2D array and 3D array to improve the reliability and so on. So now the question is really, can we use this tool for the field application? So to go to the field application, we played with plants, sorghums especially, for a long time. So we used the gas chromatography and mass spectrometry tool to see, what kind of gas is coming out. And so one is red line is blue line is before, and red line is after you started cutting these leaves. And then you see the differences here in hexanol and also here in indoor. So we decided to detect these two gases. That means we have had to redesign these new linkers. And then for field application, only the chip doesn't work, so we need to integrate the system. So this is a second generation device. I'm sorry. So second generation device where we, So we added the wireless tethering and the signal processing units, and also the sensor all integrated together on top of a battery. So this is generation 2, has a size of a deck of a card. It's still big. And then it is communicating 70 meters in the farm. So in the open space, it can go further than that. But in the farm, we found out that it transcommunicates 70 meters away where wireless gateway is located. And then from wireless gateway, from 4G or 5G, you can transfer data to your cell phone. So that's what we did. And so we have actually made multiple generations. G1 was a mug cup size, big, and second one was a deck of card size, and the third generation now matchbox size, as you can see here. Now it's a pretty small matchbox size, and everything is integrated into it. And then we have a clip on the back side so that we can clip it on actual sorghum or these crops. So one thing that I would like to mention to you is that as the gas concentration goes up, some of the analog circuits has to move together. But digital circuits, especially the MCU and the LoRa wireless tethering circuits, those two are the power sinker, big power consumers. We trigger them only at the rise edge of this voltage. And then from that point, it will operate only 10 seconds. So by doing so, we can minimize the operation period of a microcontroller electronics as well as a wireless communication tool. So by doing so, we proved that the lifetime is extended by more than 400 times in combination, all of them. This is much less than what I expected at the beginning because we have to integrate with the off-the-shelf these electronics. If we can custom design all of them, we are expecting to increase the lifetime much more. But yet, otherwise, we could use our gas sensors only for 13 hours, and now we can use it for more than 230 days. That is actually sufficient for farming and agricultural purpose because it goes more than 8 months. So we also did all the testing of on-off switching. What is the LOD? Now our LOD comes down to the 1 ppm, selectivity, and then recyclability at different temperatures. So 25 degrees C, 40 degrees C, 0 degrees C, we cycled the temperature. It all were able to generate the switching, and then up to the 99% humidity and up to the 120 degrees C, it worked. So now seeing is believing. So this is how we tested. So I'm from Utah, Salt Lake City. So we are starting from the Salt Lake City. So we sent, because in Utah, we don't have the farm. So we sent it to the Lincoln, Nebraska, who is our partner. So they have their own research university farm, which is huge. So during the summer, we tested there. And then during the winter, actually, we cannot test it there. So we decided to go to the south. So we went to actually Puerto Rico. So my students were pretty happy, as you can expect. And I didn't go, so I don't know exactly what happened. But there is a farm like this. It's a commercial farm. So they have all different kinds of sorghums to test. Some of the sorghums generate more VOCs. Some of the sorghums generate less VOCs. And then this is a sorghum farm, pretty good-looking day. And of course, in the real field, there is a wind, there is a humidity, and this is actually generation 1 prototype. If you place there, and then since we cannot bring insects with us, right? They don't allow us to bring insects, they would kill us. So we decided to simulate those insect bites by doing this cutting. So as we do the cutting, of course, please ignore the time scale on top. That's the first generation. And then, as you can see more clear, I don't know, there is no signal. So it's basically sleeping. It is not consuming power. It is just sleeping there. And then we started the cutting after some hours. Once a gas is detected, then as you can see, the whole thing woke up. And then you send the signal to my computer in Salt Lake City. So that's how I knew my students were actually working, right? So that's what we achieved in the field. So, and of course, after that, we did the generation 2, generation 3. We went out to the field, more of the field testing. And this is, for example, of the on-field spatial distribution. So those dots, 4 dots, green dots are the prototypes. And they are, green means off, blue means on. So at 0 minute, they were all off. And then the color of this box, within the box, is sampled manually in the field. And then they represent the concentration at the moment. And then we start the cutting the leaves. And then, of course, as you can see, concentration starts going up. It becomes more reddish, right? So, of course, at the center of the cutting, of course, it's more darker. And then after 28 minutes, that these first 3 got turned on one by one. So closer one got turned on first, And then as you keep cutting, it becomes really reddish. And then you stop the cutting here. And then as this highly concentrated hexagonal is spread out, the last one also got turned on. That means they are moving, following the wind. And then since we stopped cutting, the concentration of a hexagonal starts decreasing. And then eventually it becomes very low. And then all the devices got turned off again. So this testing really did show wake up and then going back to sleep in actual field under actual wind and humidity becomes the possible. And the final stage what we are working on is the localization. So we talked about network, and then still we were testing individual ones. So what we are working on right now is we are putting the network of these sensors out there. So if you look at the right side, there are 6 sensors that are out there. And then in a random location, we started cutting these leaves. And then depending on the wind direction, that the wind was blowing from the top left to the bottom right. And then, of course, it starts spreading out. And then some of the sensor, like a P5, detected first, and then P4 detected it, and then P3, P6 detected it. Based on the timing and the location of the sensors, we are trying to guess where it is coming from, right? So right now, we are in a kind of a raw stage, but we were able to localize it into about 20 square meter area out of the 300 square meter lands that we are monitoring as of right now. So this is probably what we could help the farmers. So instead of overspraying chemicals everywhere, you got to use only a small amount of chemicals at the spot of interest. So in summary, we have been developing one of the first near zero power gas sensors, normally dormant, but always on alert. That's the key. And dormancy power is 8 picowatt for a single one and 3 nanowatts for large arrays. And we use the percolation statistical control to have the to control the reliability. And of course, when we developed a single this device gas sensor unit, this is one of the first molecular breaching-based gas sensor, where we developed precision manufacturing method for the 5.2 nanometer gaps. And we demonstrated chemical synthesis and temperature humidity control as well. And then probably this is the first gas sensor really deployed in the actual field for the detection of the stress level of a plant. There are a lot of remaining questions still. So exact principle of tunneling, or what if your target gas is a long channel, it's not conductive, so the electron hopping or the tunneling doesn't happen? Can you combine the optical method? Can you measure the capacitive way? There are a lot of kind of hypotheses are now out there. Or also, if you can measure multiple different gas, then can you make the logic out of it? So that if you have this one and this one, then the gas is coming from a car, right, nearby, instead of really from the insect attacks. And also on the platform level, how we can do the self-powering more, and then we can extend it further. So right now we are supporting the battery and extending the lifetime of it. But eventually our goal is remove the battery, right? So that's the main direction we are going. So in the final, so I showed this at the beginning. There is a wonderful natural self-defense mechanism. And as a microsystem engineer, I think we can loop in. And we can improve the current state of art methods of monitoring the fields much, much better. So as a result, we can improve the crop yield and soils, and we can eventually contribute to the generating biofuel crops in a much better, elegant way. And I would like to share my final slides with you. So I'm a MEMS and microsystems researcher. Always what we are looking at is where we are going, right? So everyone is dreaming if everything is possible. People often dream of intelligent, autonomous, mobile, paradigm-shifting kind of microsystems. Maybe Tinkerbell or R2-D2 into micro versions. I think that's what everyone is dreaming, and many of us. To make it work, we need a computation, we need the actuator, we need the communication, wireless tethering, we need the sensors. But the problem is all of them have to be supported by power. Energy harvesting could be a good way if we can revolutionize it further. Or we can find the new power source like the Professor Dr. Lewis is working on. My work was actually just on top of a battery. We are trying to integrate beyond the sensor to the communication units. That's what eventually I have been working on. But in the future, what we needed to move on as a group of microsystem technology lab or community is that eventually we needed to add the mobility and also computation as well. No one is doing, well, maybe someone is doing the ultra low power AI machine learning systems, right? Right now, power is not an issue. But eventually for the microsystem engineers, these are the directions that we need to move. But all of those are associated with the power, how you are going to manage that. Maybe we got to make a micro robot, wake up micro robot, only when it is needed, it wakes up and shoot out one burst of the power, right? So those are the directions that I think I wanted to share with the students and so on. So I would like to thank the major sponsor, DARPA and ARPA-E. Actually, this ARPA-E contract, the program manager is here. Dr. David Pepson is here. he had a vision of these technologies for agriculture. And also, personally, I would like to thank Professor Tayo Akinwande. He was my mentor when I was assistant professor for the DARPA Young Faculty Award. He was my mentor. Thank you for coming. So I really appreciate all the people who contributed here, including all my students and funding agency, and also University of Nebraska, Professor James Schnabel, and so on. So with this, I would like to close my talk. And if you have any questions, I would be happy to answer. Thank you very much.
Thank you, Hanseup, for a very, very interesting talk. And now the floor is open for questions from the audience.
Excellent talk. I really appreciate. It seems you get your selectivity or specificity by targeting one particular molecule. But if you have different crops, will they all have the same type of odor that is coming out in response to injury, if we call it injury or attack?
Yeah, thank you so much for the question. The question is basically, all the crops are shooting out the same gas. Actually, nobody knows. That's what Bayer, one of the egg company, is asking us to do it for them, but we don't need to do it because we just need a GCMS. It's not our jurisdiction. So they want to survey, depending on the attacks or the stimulant. It could be just water, lack of water, or over nutrients, or deficiency of nutrients, or the physical attacks. We believe it will generate different composition of gases. So when we make a sound, it consists of multiple frequencies, right? That's combined, that's the sound. Just the same way, just my personal opinion, it's a composition of gases that as a whole could work is working as the language. So we don't know until we survey all the possibilities and combinations of it. But I think that would be something that really collaboration or the big partner is needed for that. And let's just say, if all kinds of gases are coming out, can you distinguish all of them? So this is our plan, my plan. So vertical side is chemistry. So depending on the chemistry we use, we can distinguish some groups. But on the x-axis is actually the length. So depending on the length, because we are using the nanogap, so that if we have an array of these different gaps, then we should be able to distinguish within the same group of these different lengths of gas molecules. We believe. Whether we can do it or not, of course, we gotta see.
Thank you for the excellent talk. I have a question about your linker. So when the linker captures one molecule, and then you do the sensing, after the sensing, and suppose the concentration goes down, does the linker automatically release that molecule, or do you have to do something?
Yes, so there is a very subtle balance about it. So that's a very good question. So right now we are operating this sensor at room temperature. And I'm not a chemist. According to our chemist partner, currently it is capturing the targets only temporarily. So it is actually what is happening is within the gap, indeed there are multiple sites of these linkers. So some of them are coming in, captured and leaving. Some of others are coming in and going. So it is in real time, a lot of them are coming in and out. So what we are measuring is actually equivalent to the net capture, right, of it. So the lifetime limit of our current sensor is because some of the molecules are captured, and then we are applying the voltage, right? So the voltage and then the chemical together makes sometimes the permanent bonds. So it stays there permanently. So that is limiting the lifetime of our current sensor. We believe that this is good enough because we can repeat it by 10 times, and I don't think herbivore attacks will be more than 10 times. But for other applications, for more frequent measurement, that is the biggest sore spot on this type of devices. Thank you.
This is now to look at how much current if you can go to the extent of being able to specify just one bridge, two linkers and the molecule, how much current can it potentially carry?
Yeah, that's a good question. That's what we would like to answer. We couldn't find it. Main reason is we don't have a STM, and then we cannot surface it. And then, so basically what we needed to do is we got to calculate the density of the linkers, and then when we bring the STM, and then we calculate the current divided. We actually couldn't measure it. We don't know. We don't have that information. Therefore, we don't know exactly whether tunneling is the major issue, or the electron hopping, or ohmic current, which one is really contributing this current flow yet. Yeah. So that's a great question. Thank you.
Well, I have a question about the manufacturing. So you mentioned you have made eventually like a 3D array, right? And then you mentioned something along the lines that, well, you simulated that, and it was not really surprising information, right? So like it kind of like was what you were implementing. So I don't know if you would like to share with you some insights. You know, just think it out loud. You know, there are these phenomena like vorticity that's inherently three-dimensional, and you can exploit the three-dimensionality to make it better. You know, and that's why perhaps making three-dimensional mixers or combustors makes sense, right? But in this case, what do you think didn't really add on? I mean, I understand it added on in terms of performance, but perhaps not like in a unique way to connect the different parts.
I'm not sure I understood your question, but you are asking me about the what kind of benefits or future use of the 3D structure. So we are building 3D structure because of obvious reasons, right? We need to lower the bias voltage so that we don't need an additional circuit which will consume our power. So that the power is the most sensitive part. And then second is, as we saw in the previous slide, you know, as we increase the array size, the minimum detectable concentration, or LOD, is going up. So we need to lower it down further. So in a larger array, we want to lower, this is too high, so we want to lower it down. That's why we are using this 3D structure to increase the degree of freedom. And according to the simulation, increase the degree of freedom will lower the threshold. So that's the reason why we are using it. Now, how we can best use of this structure is related to the, I guess, how efficiently we can flow things through the 3D structure. So right now, 3D structure's performance is probably limited by the speed, right? I did mention about the speed. So as you make it more complex, so gas should be able to go in and out pretty quick. That determines your response time. So how to design your 3D structure with more space, or that basically increase the flow conductance could be the next task, or something that we can play with.
Thank you. Any other questions from the audience? Okay. Let's thank the speaker once more.
Thank you.
Thank you for
Thank
your
you.
excellent talk, and I'll see you next time in the next MTL seminar. Thank you.